velocity here. So if I release one spring, push the object here at a smaller mass, I'll get one velocity. Now if I release two springs, then I will get 2 units of velocity. So whatever the velocity is, it'll be twice the velocity. And then 3 springs will give me 3 velocity. Okay. Now it's just an undisputable fact that I did 3 units of work. I didn't do 9 units of work. I just did 3. These are equal pressure that I applied to these springs and locked them with that pressure, and that's all the energy I put in.
All right, let's now explain in little baby steps for Gary why using 3 springs won't give us 3 times the velocity. Step 1. What a spring actually does. When you let go of a spring, it pushes the object, but only for a short time while it stretches or squishes back to its normal length. So the spring doesn't just give a shove, it gives a push over a distance, and that distance depends on how much the spring was compressed. That push over distance is what we call energy. So energy equals how much total pushing the spring can do while it moves the object. Step 2. What happens as the object speeds up? As the spring pushes, the object goes faster and faster. But here's the tricky part. As it goes faster, it leaves the spring sooner. That means if the spring is twice as strong, yes, it pushes harder. But the object speeds up faster and escapes the spring in less time, so it doesn't get twice as long of a push. The spring gives more total push, but not enough to make the speed double. The extra strength gets partly canceled out because the push happens for a shorter time. Step 3. Why the square root rule shows up. Let's imagine an example that's easy to picture. Suppose one spring makes the ball go speed 1. If you add another identical spring, the total energy push over distance doubles. But the ball leaves the spring faster, so the total push doesn't double the final speed. It increases it only by the square root of 2, about 1.4 times. You can think of it this way. The spring's energy decides how hard and how long it can push. Doubling the energy means twice as much total pushing, but since the object spends less time in contact, the speed only goes up by the square root. Big idea in one sentence. Making an object go a little faster when it's already moving costs more energy than making it go that same amount faster from rest. That's why doubling the final speed needs a lot more than twice the energy. Why each extra little bit costs more when you're already moving. Here's the key physical idea. No math. When a push happens while the object is already moving, the push does work while the object moves forward. The faster the object already is, the farther it moves during the push. So each little push delivers more work. It gets multiplied by the object's motion during the push. That means pushing an already fast object increases its stored motion more quickly per push. So to get a fixed extra amount of speed now takes more total energy overall. Put plainly, when the object is slow, a fixed amount of energy gives a certain speed increase. When the object is fast, that same fixed amount of energy gives a smaller speed increase. So to get the same speed jump, you must spend more energy. Imagine pushing something light on the floor. You give a gentle, steady push to get it going. At first, it's easy. You see it start to roll faster and faster. Now imagine doing that again, but this time it's already moving fast. You try to make it go even faster with the same push. What happens? You notice that your push seems to do less and less to its speed. Even though you're applying the same strength, it barely speeds up anymore. Why that happens? The less effect of each push. When the object is slow, it's easy to give it speed. Every little push feels effective because it stays under your hand longer. When it's fast, it flies out of your reach sooner. You have less time to push before it's gone. So, with the same effort, same push power, the faster object receives your help for a shorter moment, so it gains less new speed than before. Picture a car analogy. When your car is going 10 kilometers per hour, a small tap on the gas pedal makes it noticeably faster. At 100 kilometers per hour, that same tap barely changes anything. You need a lot more fuel to get from 100 to 110 than you needed to go from 0 to 10. Why? Because the car's engine has to keep pushing against motion that's already strong and moving forward quickly. The same push doesn't last as long. The effect on speed gets smaller and smaller. The inevitable result. Each time you double your speed, you must buy that extra speed with a lot more energy packets because you get less time to push, each push adds less extra speed, but you still need the same total change in motion. That balance is what makes the relationship come out the way it does. Going twice as fast demands 4 times as much push energy, not because math says so, but because the faster you go, the less each bit of energy can still help you accelerate. All of this has been verified by physical evidence. Michael Fowle and myself have done this experiment, but instead of launching the mass with 1 spring, then 2 springs, then 3 springs, we launched a 1 mass, 2 mass, a 3 mass, and a 4 mass, each time with the same spring compression. This basically is the same kind of experiment, just the other way around. Now, Michael did it vertically, I did it horizontally. Both of us got the same results. The results showed that the velocities or the peak heights follows the square root principle. When a 1 mass is launched, you get 1 unit of velocity. When a 2 mass is launched, it will go around 1.41 times slower, not 2 times. When a 3 mass is launched, it will go around 1.73 times slower, and when a 4 mass is launched, then it will go twice as slow. Thanks for watching, people. Except for Gary, any explanation, any piece of evidence, no matter how many times we do it, no matter in what way, it's all absolutely pointless.